Okay, so hello and welcome to this video tutorial for RC Hibbeler's Engineering Mechanics Dynamics textbook. So we have this problem from chapter 14 of the textbook that's asking us it's saying the 2.5 kilo collar is pulled by a cord that passes around a small peg at C. If the cord is subjected to a constant force of F, which is equal to 50 newtons, and the collar is at rest when it is at A, determine its speed when it reaches B, neglect friction. So this is quite a wordy question that we have here, but let's just try and unpack what's going on a little bit. It wasn't immediately obvious, at least not to me when I first saw this diagram, what it meant. What it's basically showing us here is we have the kind of initial condition where the collar is at A. The collar then displaces 2 meters and then has this kind of final condition here at B. And we're being asked to determine the velocity of the cord when it reaches this final condition here. So to solve this problem, we can make use of this idea that I've shown below, where we can say this is just kind of like a conservation of energy idea that we have here, where T subscript A can be taken as the initial kinetic energy of the object, TB the final kinetic energy, and this sum of U subscript A minus B can be taken as the sum of potential energy changes for our object here. Or in this case, we can effectively kind of take that as the kind of work done by the rope in this context. Naturally, if we want to determine the work done by the rope here, we want to kind of determine how far the rope pulls. Since we understand that work is the product of distance and force, right? Work equals force times distance. As our collar moves from point A to point B, this force is carrying out work. So what's of interest really to us is kind of the difference between, let's pick a different color here. The difference between this distance, let's call it AC, makes sense, and this distance, BC. Okay, so we want to determine the difference between those two forces. How we could do that, we could have our kind of initial condition. Let's have a look here. So in our initial condition where our collar is at point A, we can say that this length here is 2 meters, that this length here is 1.5 meters, and so this length here, AC, we can say AC is equal to the square root of, in this case, 1.5 squared plus 2 squared, which is equal to 2.5. Okay, so we can say that AC is equal to 2.5. BC is effectively already given, right? So BC is evidently 1.5. So we can say, therefore, AC minus BC, or in other words, the distance that the rope is pulling is equal to 1. Okay, since 2.5 minus 1.5 is 1. Okay, we can go ahead then and use this idea that we have here. So what's our initial kinetic energy? Well, evidently it's 0, since the question points out to us that the collar is at rest at point A. So our TA can take a value of 0. This term here describes the work done by the rope. So it's going to be the force times the distance here, which is going to be 50 times 1. Let's just call it 50. And TB here, our final kinetic energy, well, we don't know its velocity. That's what we're trying to find out here. But we do know that we can describe the kinetic, we can describe kinetic energy as half mv squared. We have the mass here, it's 2.5, so we could say half of 2.5 times velocity squared. Okay, let's call it VB. We can rearrange this. We can say we have we can say that VB is equal to the square root of well, if you multiply both sides by 2, we'll give 100, and then divide by that 2.5. We have the square root of 100 over 2.5 here, which gives us a value of 6.32. And this is a velocity here, not an energy, so we can say this is meters per second. Okay. If you have any questions or comments about that problem, please feel free to leave them down in the comment section down below. Otherwise, thank you very much for watching.